some big numbers. So, all right, well, speaking of numbers, segue. And backing up a little bit, we've talked about our understanding of dark energy and dark matter and atomic stuff. More recently, we thought it was like 72% or so dark energy, 23% dark matter, 4.6. Our modern understanding is a little tweaked as,
John,
yes?
If they can't measure it, how do they know there's more dark energy than dark matter, or more dark matter than dark energy now?
The dark matter is estimated based on the amount of gravitational lensing is one technique that we see at distance.
It has several attributes?
It's,
dark stuff?
well, we don't know that, yeah. That's a cover-all term. The dark actually, in one way, it refers to the fact that it doesn't interact with electromagnetic radiation. So whatever the phenomena is, or particle, or material, or is, it's not affecting the transmission of electromagnetic radiation. But it's also just outside of our understanding. So, yeah.
I just thought it was curious that they divided the two into the two things that we can't see or measure or really know that it's there.
Right. Well, and I'll go over here. The dark matter percentage there, that is linked to curvature of space-time. The material that has mass does. Dark energy is quite the opposite. In a way, it acts like an anti-gravity force. So it's an expansion rate. So you can look at the acceleration over time of the universe and figure out how much anti-gravity pull or push, I guess you'd say, depending on the point of view, push it would take to accelerate space-time that much. And so then you crank it through probably just the equations of general relativity to figure out what the E equals mc squared energy equivalent is. So then you add up what you think you got in normal matter, dark matter, and the rest is going to be dark energy. And of course, this leads to the curvature of space-time, which kind of goes to the Library of Babel talk, in that how big is the universe is related to how flat it is. If it's highly curved, then it's not going to be that large. It could be far beyond the horizon of our observable universe, but it's going to come back around, at least in theory. It's a closed space-time system. But as you get wider and wider and wider, flatter, 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 you are pushing the possible size of the universe up towards infinity. So, and this is what we find. We find a very, very flat universe inside our bubble that we can see. So we do ask questions about the Big Bang, like before the Big Bang, was there another universe that collapsed and bounced out? Is our universe finite but unbounded in time? So finite would be something like a more curved system. Even if a little bit of curve is still finite, it's just gigantic. So, and that of course depends on your favorite theory. We talked about the progression through the Big Bang a lot, so let me keep moving here. So the early questions were, how curved is the universe? Because if it is curved enough, it's going to also collapse back. So it's a closed universe. So eventually there will be the big crunch. If it's open, if it's in this region here, curved somewhat, but not too much, then it'll just keep expanding. Matter will not be able to pull things back. And it was this investigation, which side of this line are we on, that was being conducted when we discovered dark energy. And once we found that there was an acceleration to the expansion. This chart is just trashed. There's no close, there's no bouncing back unless the very nature of dark energy changes in the future. But since we don't know what it is, we can do nothing more than speculate. But there are theories or hypotheses that are painted out there where at a certain low density, low temperature, dark energy may reverse its effect and pull things back. But it's just speculation. It really have very little to go on it. They just want to cover the bases, cover the possibilities that are out there. So again, 26.8%, 83% for dark matter, just under 5% for visible or observable matter, and 68.3% for dark energy.
Hey, John?
Yes? Oh, sure, absolutely.
Go ahead.
All right. So, looking at the Big Bang problems, how flat is the universe? And we are very close to completely flat. The background radiation that we saw left over from the Big Bang is really uniform. From opposite sides of the sky, which is opposite sides of the universe, the temperatures are correct within 1 part to 1,000. That's really good. I mean, even nothing in this room is that uniform in temperature. I can guarantee it. And so the horizon problem says, how do we get things that similar across the universe when they're not connected? I mean, right now it takes 26 billion years for information from one side of the universe to reach the other side. And that a lot happens to radiation or information in that amount of time. So that's not a way you can sync the universe. It had to be something that happened early on. And the solution is the inflationary period. That the universe was extremely tiny, everything was essentially in contact with every other part of the universe, and then in that time of in contact sameness and smallness, it inflated really fast, and it just froze that sameness into the universe at whatever unlimited distance you want.
John, is that anything like the bit where you've got an electron or whatever here, you split it or you take its buddy and you move it over here?
Oh, entanglement?
Yeah, entanglement. If it was entangled at the beginning, it would have to be a really fast expansion.
If that were the case, that would, you see, yeah, it wouldn't work because of the extreme high temperatures and densities that the Big Bang would have at the beginning. Entanglement is an isolation effect. So you can't have other things jostling the particles or imparting information or taking information away from the system because the entanglement is instantly destroyed. So, yep. So good question though, you're thinking. So the theory is, going back in time, back here, that, you know, present day we have these four happy forces: gravity, electromagnetism, weak and strong nuclear force. As you go back towards the beginning, when the temperatures rise unbelievably, I think there's temperatures in Kelvin, so 10 to the 15, 10 to the 27, 10 to the 32 degrees Kelvin. That's just, we don't see temperatures like that today. I mean, sometimes Phoenix feels like that, but it isn't. So back at this temperature, electromagnetism and weak force act like one force. They unify. And we have figured out the equations to describe this state. The electroweak force is known mathematically. What we are looking for is back here, the grand unification theory point, where electroweak and the strong force join in one. That would be the grand unification force back here. And this would occur before this inflationary period. So this is back when the universe is so small, so dense, so hot, and everything is in contact with each other. And you just have that force and one other weak little gravity over here. We don't have this figured out yet. We haven't been able to extrapolate reality back to that junction point. So it is still theoretical. And then what we'd love to do is bring gravity into this mix, but that's even higher temperatures, even more speculative, and we don't have that either. So we are looking for the superforce. We're looking for this, put it all together into one thing, and that's what we're going to spend some time doing shortly, is looking at the major approaches to how to put these all together. We do have the concept of the vacuum energy in the universe. If the universe is not at its lowest energy state, as this little model shows, we'd be up here on top of this hill in the middle. It's a false bottom. We can measure the amount of energy in empty space by looking at the virtual particles that are coming and going in empty space. That these are a frothy, seedy little byproduct of the fact that the universe is suspended above a ground state of absolute nothingness, basically. So that's the Casimir effect. I think, do I have a picture of that? Nope. Casimir effect, I talked about last time, right? Remember? Okay, Casimir effect is observable in pretty simple tabletop experiment, actually. It also is needed in the equations that describe and the physics that describes the subatomic world. The virtual particles are being exchanged in force transactions. But what you basically do is you get a box with a great vacuum, and you get a couple plates, and these are really good, very, 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 very smooth plates, and you bring them closer and closer and closer together. In empty space, these little virtual particles are coming out of nothing, out of the energy that's available in empty space. They are particle-antiparticle pairs, and then they rejoin and annihilate each other. And they create energy when doing that, but they've left a hole in space-time of the energy that they borrowed to come into existence, so that just goes right back into the bank. So they borrow, they go, wee, oh, and they meet each other again, it's gone, energy goes back into space, and that's it. Space-time is seething with this across the entire universe. With the Casimir effect, between the two plates, the two little particles eventually don't have room to do their little travel apart in the direction that the plates are coming together. So they can only do it in the gap direction. But on the outside of the plate, the little particles are doing that against the outside of the plate in all the directions they possibly can. That results in a net inward force that you can measure. You can measure the plates being slightly pulled together, or pushed together really, by the virtual particles outside. So I've considered writing a science fiction story where an advanced civilization is spreading through the universe and is using this energy somehow in a way that threatens to nudge the universe in some spot off of that, which would cause a cascade failure of space-time at the speed of light. A bubble would expand, annihilating everything. Everything would be converted to energy. So, well, yeah, so a little upstart civilization like Earth in 100 years from now has to go up against this big, unbelievably advanced group and somehow save the universe. So, who knows? I got ideas. So here's the universe starting. This is the Planck era, when the universe is down the size of a Planck volume. Then it starts to expand. Then you have the expansion period where the universe greatly increases in size far beyond the speed of light. Empty space can increase in size faster than the speed of light. You just can't get stuff and energy to go faster than the speed of light. And then it cools and cools and cools. You have the weak era. When that ends, particles can form. Then nuclear synthesis occurs throughout the entire universe, like it does in the core of a star. And then it cools enough that nuclei can start to form like the outer part of a star. Then you've got the point where the universe transitions from hot opaque to transparent, just like the surface of a star. And then eventually atoms can form because the universe cools enough that electrons can settle down into the atoms. And then first galaxies are born, first stars come on, and the ultraviolet high energy radiation from stars begins to knock electrons off. So you get the period of ionization. Galaxies are forming around the streams and clumps of dark matter left. But all of this goes all the way back to the clumpiness in the quantum weird soupy world of the very early tiny universe. That's our big picture of the history of space-time.
Question about the inflationary period. You said it could happen faster than the speed of light.
Yes, oh, far beyond.
Because there is no light to have that speed limit.
No, electromagnetism is tied up as a different force, and whether there is a speed limit to processes, I don't know that. I would guess the speed of light still applies. It's space-time itself that's increasing in size, though. So it's nothingness or the emptiness between things that is doing all the increasing. It's extremely speculative, but the particle is named the inflaton. So that would cause this inflationary period. So the inflaton would be a force transmission particle of the grand unification era force. So probably obeys the speed of light, but magic happens.
So to simplify it from my little brain.
Yeah.
So space-time itself is expanding,
Mm-hmm.
inflationary. I don't know. I have
Yeah.
a lot of trouble figuring out how big it is, but basically it's carrying along everything else along with it.
Right, just exactly the same process we see today, that a galaxy that's so far away from us is moving away from us at a certain speed. One that's twice as far away from us is moving at twice the speed. So the emptiness in between is increasing. So the galaxies appear to be traveling away from each other. But faster with distance. So further distant points in this early universe are being carried away from each other faster too. But this is, trillions and trillions of a second that you're getting the universe increasing 20, 50,000 million times in size. So it's an unbelievable, hard to envision expansion in trillions of a second. So.
I guess my question was, to have light,
Mm-hmm.
you have to have subatomic particles that are being ripped apart from each other, I guess, to get that energy to produce a photon.
Mm-hmm.
And in that inflationary period, were there elementary particles that could produce light to do that?
Right in this area, they have question mark elementary particles and elementary particles. So were there quarks, were there electrons, were there gluons? And gluons are part of the strong nuclear force, which doesn't freeze out till later, right here. Is it the inflatons then? And
So we're working under a whole different
Oh,
type
yeah.
of physical
Right. Yeah, that is,
constraint that
right.
the speed of light doesn't really exist. It's just,
Or we don't know.
or we don't know.
Yeah.
Good.
I would, if just made to guess, I would still say that the speed of light, just because light is what we play with now, is built into this construct from the beginning.
Yeah. Well, I was reading somewhere that there are 6 constants
Yes.
that constrain our universe.
Mm-hmm.
And was that a period of time where those constants did not exist? And
Probably, yeah.
It was formed.
The fine structure constant, you got the speed of light, right? The fundamental unit of charge. Good questions. You guys are thinking.
Won't last long.
Yeah. Yeah. But see, with
I think I blew it all.
yeah. Without a grand unification theory and without merging gravity and having a quantum gravitational theory, we really are shooting in the dark. I mean, we really don't know. We still want to answer the question like, what's inside, what's just under the surface of a black hole? What's happening right at the surface of a black hole? We have some progress, and we'll talk about that later, but with Hawking radiation like that, but we need verification, and we need observation, and there's a lot we just can't yet push into. I mean, what is happening at the dead center of a black hole, the singularity? Is there a singularity, or is it a different process that kicks in?
So we're way up in the top portion
Yeah,
of that.
yep. This is our present day up here.
Looking back to the Big Bang, we can only see to the plasma, hydrogen, and helium nuclei.
Yeah,
being formed. We can't see through that.
in electromagnetic frequencies, looking at microwave radiation, this is the boundary. Looking at neutrinos, we can go in, because neutrinos will sail through that. Looking at gravitational waves, we can go all the way back into here theoretically, yeah. So we are looking at like the B mode pattern on this surface would give us an indication of what gravitational waves were doing in the much more dense universe back here, and let us see, by looking at the surface here, all the way back. Could we someday get gravitational wave observatories that can directly observe these? I mean, they are very, very weak. So I guess theoretically, yes, certainly not in any of our present day technology. But we can look at what the gravitational waves did to the distribution of this material as it's printed here. So a lot of research is looking very closely at these subtle temperature changes that are left visible to us and patterns in them, things that are off random. Yeah.
So I know this is kind of a big, wide open question.
Okay.
Being able to look past that plasma and into gravitational waves, what do we get out of all of this? I mean, do we form energy based on gravitational waves that we can use to travel the universe at the speed of light? Or, I mean, is there any practical application?
Yeah, a lot of this, I think, is driven just by that hungry curiosity. But at the same time, when we have figured out a new fundamental aspect of the universe, whole new things open up. I mean, nuclear power and nuclear weapons all came out of the discovery of the strong and weak nuclear force. So, which Einstein stood on the transition point in human understanding of that and decided not to follow everybody into that new world. But yeah, so that's, look how incredibly recent that is. So, but
That's one of those things where you go, the amount of brain power that's being pointed backward to figure out where we came from and where all of this came from if that were pointed at where we are now and solving,
We'll possibly go.
or possibly going,
Yeah.
Is it going to be of benefit to humankind
Mhm.
to know what it looked like or acted like way
I,
back there when
Right.
we've got so much right here, right
Mm-hmm.
now?
yeah, well, I think, curiosity is certainly built into humans.
Yes.
And curiosity is a random thing. What people find lights their fire is infinitely variable. And so I don't think you could in any way get someone who just stares into the night sky as a kid and wants to understand where it all came from to arbitrarily divert. So I don't think there's any mechanism to do that. Right. I think to look up and see the stars does that to a fraction of the people out there. So, and you never know what they're going to discover. You never know what the applications are going to be to the discoveries.
So what, besides nuclear weapons, what have been some of the other applications or discoveries in this type of study that we have now that we would not have had if they hadn't been doing that?
Well, in astronomy in general, the understanding of neutron stars, what they are, and how regular they are, has given us a future galactic GPS system. So rather than satellites around the Earth, you have now a navigational timekeeping among the stars. So if we do go out and start exploring, or our robot descendants do, they will have a great way to do that. We understand why, we know what the physics is going on in those systems. We certainly understand a lot more now about where the Earth came from, where materials and elements come from and why. And so I could probably think of a lot of other things, but
The field of quantum mechanics really came out
yeah.
From looking backwards?
Yeah.
of solid state.
Yeah, all of our smart devices.
Where my paycheck comes from.
Yeah, all of our smart devices and like that are all based on detailed understanding of the basic physics that drives us. Yeah. So a pretty picture there.
So hopefully nobody wipes out the entire universe if they look too deep.
Right.
That would be our.
Right.
Exactly.
But yeah, there's two.
In time, so maybe we can go back to fix all this.
That's true.
Yeah, but you have to travel before they destroy it. You gotta know they're gonna destroy it and travel back to fix that part.
Yeah, and there's two scenarios like that could end us without us even knowing it. Would be if some point in the universe fell off the faults or energy point into a lower depth, you'd have a bubble expanding at the speed of light that would just annihilate everything. So you wouldn't see it coming. It'd just be one day you're gone.
You look around and you're going, oh.
Another thing would be if in the models where we have higher dimensional separation of other universes like ours, they can touch theoretically, and if to touch, then you'd have a hot bubble of annihilation heading out from the touch point at the speed of light, which you wouldn't see either until, in theory, until it just takes out everything.
Because it could not necessarily, I mean, it could maybe do something totally different.
Yeah, there's even, I saw a paper once where they're looking at distributions of galaxies across the sky, and they speculate that an anomalous clustering of galactic clusters, often distant part of the universe, may signal that there is a partner universe not far away, and that the two are influencing each other some. So it could have a trans-dimensional gravitational tugging going on that we can see printed across the sky. That's going way out on the plank of speculation. So, All right, so we've kind of hit this really well, so let's keep on moving. We talked about the end. Let's get to the end of sort of past, present, formation of our solar system about 9 billion years ago, and sorry, formation of our galaxy. I should be galaxy right there. 9 billion years ago in our solar system 4.6. The habitable epoch is about 375,000 years. What on earth is that number?
After the bang?
Oh, after the bang. Yes, thank you very much. So once the universe cooled enough that you could get stuff forming, like stars and matter coming together, you're in the habitable time. End of our solar system, about 1 to 5 billion years from now. The 1 billion being the sun starting, very noticeably expanding and heating and cooking things. Orbits may become unstable. We believe the sun will swell and almost certainly swallow Mercury and Venus. The Earth is debatable when we model it different ways and take in different effects. The sun gets bigger, you have more drag. Earth gets swallowed. But the sun is throwing off its outer atmosphere as it does this, so there's less gravitational pull, so the Earth's orbit expands a little, so we don't get swallowed. So you play little games, but we're really close to the go or no-go point in the solar system. Mars makes it.
The mention of Mercury. The probe that, I think it was just launched,
Mm-hmm.
to go to Mercury, to check out the ice on Mercury.
Mm-hmm. I know a little bit about it. I was just starting to do my news update, and I was looking at that as a possible story focus, and I realized we weren't meeting, so I stopped. Like, I got lots of other things to do. I'll save it for the future. So I didn't read the article fully, so
Okay.
sorry. We know that the Andromeda and Milky Way galaxies will merge in about 5.5 billion. That's about where the sun really stops resembling our present-day sun, and things get really nasty around here. Other ways that even if we head out into the universe, if the it gets worse. If the dark energy continues and is a certain acceleration rate, which we're, again, really close to this decision point, we're going to need more measurements. But we get the big rip about 20 billion years from now, and this is where the present-day expansion between galaxies and clusters of galaxies starts to become so pronounced that it can overcome the gravitational attraction between galaxies in clusters, then eventually overcome the attraction between galaxies that are close, and between the stars in the galaxies, and then between the planets around the stars and the galaxies, and eventually pulling planets and stars apart itself and right down to rocks and the molecules and electrons out of atoms. And so the expansion of the universe just goes on a runaway until everything gets pulled apart.
Is it really a rip like we think of?
It's empty
Or
space.
is it simply things floating away, like when you blow on a dandelion and they don't hold together anymore, they just...
It's empty space exponentially increasing. So it's like putting a whole bunch of pieces of paper on a balloon, and you start blowing it up, and then you blow it up faster and faster, then you just blow it up until it is doubling in size every fraction of a second, and then every billionth of a second. So it's like things are spreading apart all the way down to the smallest scale, up to the speed of light and beyond. So
atoms.
yeah, atoms that eventually get pulled apart. Yeah, everything gets pulled apart. Everything that isn't a fundamental particle would get pulled apart by the expansion of space-time. That's the big rip. The big freeze is where most of the available star-making material has been used up. Galaxies are already kind of running out of it in places in the universe. There's only so much. Once you start making lots and lots of iron ash and neutron stars and black holes, you have less material for making new stars. So possibly about 100 billion years from now, the universe will start to really go cold. Heat death is where entropy completely rules. 10 to the 1,000 years from now, we talked about some of these in my big numbers talk. And the vacuum metastability event, that's related to falling off of that false bottom, that the universe would just eventually do that. So.
Okay, wait a minute, John.
Mm-hmm.
I'm a little confused. More than a little.
Okay.
So the big freeze happens even after the big rip, or is that?
Big freeze is where basically you don't get any more new stars, any more heat sources.
There's a big rip, there's no stars left, right?
Right, but this is speculative. We don't know if this will.
So that might not happen.
It might not happen.
If that doesn't happen, then okay.
Yeah, then we move on to that way to die, or that way to die, or that way to die.
Technology there.
That's right. Yeah. So it's stacked against us.
And you've got a freeze and then you've got a heat death.
Yes.
This sounds like a good novel.
Well, eventually it becomes really boring. Because if the passage of time is related to entropy, as we'll play around in a little bit, once you have no more heat transfer occurring from one spot to another, time doesn't run anymore. Yeah.
Time depends on heat.
Yeah. Very possibly. The arrow of time, the direction of time, comes from the irreversible processes dictated by entropy. And we'll talk about this. I've got this in slides yet to come. So.
I think you just made that up.
Well, I made it up before I made slides. So what else does having a grand unification theory help, or even a quantum theory of gravity? Was playing with the present day problem of how Einstein's general relativity and the theory of quantum mechanics, the two big pillars of scientific understanding, don't work together. We don't really understand everything that we need to understand. And it all comes down to that singularity that I've hinted at a number of times, that is this a point of infinite density? What happens to space-time? What happens to energy? What happens to the concept of temperature when you're crushing stuff down to infinitesimal size? Are you creating another Big Bang? Is this popping out new universes? Which is a valid theory out there, is that universes that can make black holes continue to make new universes. And in that way, universes are a constantly self-propagating process. Ones that don't make black holes have a one-way dead end, and they don't have any universal progeny. So we are special in that we're birthing universes in that concept continually. Every time a star dies, a universe is born. It's very, very poetic.
So you're saying a star that goes into a black hole pops out as a Big Bang somewhere else?
Theoretically, yeah. So, and looking at this curvature of space-time, this is parts that I'm still trying to get my brain around. So gravity is a force, and we're playing around with gravity in the same way that we play with electromagnetism, or electroweak, or the weak force, or the strong nuclear force. But then we have this other way of looking at gravity, which any of those can be considered a field as well. So electromagnetic field, electromagnetic particle photon. The weak nuclear field, or W and Z bosons, or the gluon for the strong nuclear force or field. There's a field way of looking at all forces. And this is a field way of looking at gravity. But yet it's also the curvature of space-time that we're immersed in, that we're part of. So I, in my brain, still don't reconcile these two viewpoints, other than I just know that these are all valid ways to look at gravity. That's why one of the presentations I'll do in the years to come is what's so heavy about gravity. And I'll go into all the different ways that we look at gravity and the problems that we have with gravity. I'll get into gravity as a topic all by itself. Unbelievably weak, but yet shapes the entire universe like all the stronger ones don't. So there's some weird paradoxes here, so at least in my head. But with the model of gravity curving space-time, it's really hard to visualize a three-dimensional volume curved in both time and space. And I say it's curved in both time and space. It really is. That where you have the Earth underneath us, if you want to make equal little imaginary cubes of space, as you get down into the Earth's gravitational field, these cubes are smaller. Get closer to the sun, the cubes are even smaller. Get to the surface of the black hole, and the cubes become really small or vanish. I'm not really sure how to handle that in my model either. But time itself is slowing as you go closer to a gravitational source. So the clocks down here from general relativity are running slower than they do out in between the galaxies. On the surface of the sun, clocks are running even slower. At the surface of a black hole, events stop happening because time stops flowing. So again, we have just a couple slides back, time being related to the game entropy plays in the transfer of heat in the universe, and now we have time related to the curvature of space because of gravity and mass and energy. E equals mc squared.
That they have measured with clocks on the Earth.
Oh yes, very well established. And like I said in this talk, and I'll say when we get there, is that the equations of general relativity are in here. Otherwise, the GPS unit wouldn't work. And so the passage of time at the height of the satellites is different enough that this would be useless in just a week or so. You would be way across the field on your GPS map, and then ridiculous answers after that. So we know we're immersed in this, I wish I had the quote, wibbly wobbly, timey wimey stuff. That's not exactly Doctor Who's quote, but that's close, yeah. It's become quite the meme. But this is what we're going to deal with. We're trying to reconcile this curvature space-time model. Here's a path of light coming past a big star of some kind. Here's an orbit of something else. Here's something orbiting out here. And so here's the surface of a star, our sun. So you can fall in, space-time is curvature, because then you get all cooked in high temperatures there. Around a white dwarf, which is right down here, it's hard to see it, it's curved below the map representation. Curvature is really extreme. So as you go down in there, space-time is tugging on you so differently. The rate of time at your feet and your head is so different. Space-time is so non-flat that you get pulled apart. Another way to look at that is a tidal force model. You say, the tidal forces on me are so different, getting close to this white dwarf, that I'm being pulled apart. It's the same phenomena, it's a different way to think about it. And then with a black hole, the stretching of space-time is theoretically infinite. It's going all the way down forever. The thing that stops you is when space is now tilted so far in the four-dimensional direction, the time direction, that time isn't passing anymore, which is another way to say that the event horizon, time stops. All the same phenomena, different ways to describe the phenomena that's occurring. And then, we're just about break time here, close. when you do take the equations down and try to jam stuff together in our understanding down at the Planck scale. Anybody remember what the Planck scale is? That's the theoretical smallest distance we can get in space. And there's multiple reasons to explain why that's the smallest, but one I like the best is when you look at a computer and you want to see what's going on with this computer here, I can use visible light to do it. Not very energetic. If I want to look inside a crystal and see the structure of the atoms and molecules in a crystal, I'm going to have to use X-rays. I'm going to have to go to higher energy electromagnetic radiation to probe it. If I want to see what's happening inside of a nucleus of an atom, and I better use gamma rays. I gotta go to extreme high end of electromagnetic radiation. Or maybe leave that and switch to beaming it with electrons. So the wavelength of an electron is really high. You got matter and electron wave going on. So as you want to probe smaller and smaller, you have to use higher and higher amounts of energy in your probing unit to do so. If you want to probe what's going on, you want to make a picture of this little cube of space-time at the Planck scale, the probe that you have to use is so high energy that it pops into becoming a black hole for an instant, for the time it takes for your probing element to cross the Planck distance. Of course, it immediately evaporates, so as soon as your probe gets out the other side, but since it popped into a black hole now, you don't get any information out of it. The information is lost in the process. So you can't probe any further. You're done. You're limited at how far you probe. The speed of light, the time it takes something to cross this final cube at the speed of light, is the Planck time. That's the smallest interval of time that ticks in the space-time that we understand. So there's a floor. There's a smallest tick of time. So I'll leave you with Planck's. We'll take a 10-minute break, 8-minute break or so, get refreshed, and we'll pick up here in grand unification theories. Yes, it does. That's funny, you don't hear about lottery winners who start this foundation or make this contribution to mankind. It's really weird.
Well, I was reading about that. Most, I think like more than 70% lottery winners are bankrupt within 10 years,
Yeah.
something like that.
They don't know how to manage it.
And how do you go through that kind of money
I know.
quickly?
People who are used to dealing with that kind of money don't play lottery.
Yep.
Probably not.
All right, so to sum up what we get from all these different theories, that all velocities are relative, and we get that from special relativity from Einstein. Space and time are both aspects of the same thing. The accelerational pull and gravitational pull are indistinguishable, and we've measured that to many, many, many decimal places. Energy and matter are the same. E equals mc squared, famous, possibly the most famous equation, even if the equation for entropy that we'll see shortly may be more important to your day-to-day life. Space-time curvature is energy, which leads out of superstring theory. So you get the bending of space has energy in it itself. You also have a pressure to space, and that also has an energy component to it. But what we see is general relativity and quantum mechanics don't mix, because when you get down into this realm and try to work it out, you get singularities popping in and out, you get step functions in discontinuous behavior, and it's just, you can't predict anything. Like, if you're going to have a particle move along here, where's it going to be 3 moments later, whatever moment you want to specify? How do you do that? It's got to go up the side of this, down that, around there. It's going to get deflected backwards. It's a mess. See, there's something we are missing in our understanding of space-time. A few quotes here from Hawking. If we do discover a complete theory, it should be in time understandable and broad principle by everyone. And we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of why we in the universe exist. So there's Stephen's answer to your question. Or your question, sorry. What's this for? Brian Greene says, no matter how hard you try to teach your cat general relativity, you're going to fail.
Because the cat doesn't care.
That's true. We can certainly go further than cats, we being humans, but why should it be that our brains are somehow so suited to the universe that our brains will be able to understand the deepest workings? So he's approaching this much for philosophical. Like, will there be a point that we just can't wrap our little primate brains around?
For most of us, we've reached that.
Well, again, going back to this, I think through analogy you should be able to explain anything. I think.
Yeah, but I never find it.
Okay, all right.
Somebody else found it.
Someone else
They
found
can explain it to me.
Well, you see, you get a bell curve of all phenomena. So
That's an evolution of the brain, maybe,
Yeah.
that's true.
as we discover things.
Or our robot overlords.
Yes.
Yeah.
Yes. They'll do it.
Yeah. Google,
Send it back to us in time.
the Google AI, well, or AGI. Yeah. But we do seem to be wired to make sense of the world around us. We do make mental models that allow us to
We're wired to want to
function.
make sense.
Hmm?
We're wired to want to
Yes,
make
that is
sense
true.
and to make sense about the world, even if it's not true.
That's true also. Now you're getting into my book. Yes, yeah, you're touching on section 1 of my book. Our brains learn by linking previous ideas to new ideas. We make categories of everything. For instance, is each green thing growing outside its own entity? Okay, if you stop there and every green thing you look at is a whole new discovery for you, and just stop and you stare at every blade of grass, you're not going to walk very far. So and it's neat to have childlike wonder, but yet you do start to need to make categories. So if you make categories of trees, bushes, grass, and moss, now you've narrowed the number of green things that grow in the world like that down to about 500,000. All right, well, it's getting better. It still takes you a long time to think about 500,000 things.
Now, on your first one there, linking previous ideas to new ideas, that assumes that our personality, our brain, whatever, is open to the new ideas.
Yes.
Because our brains can also learn by stopping at one idea and tossing anything that isn't.
Right, we are always pruning and truncating avenues of thought because there is only so much time, there is only so much memory that you can easily have access to. Yeah. Well, if you categorize further to chlorophyll being the process that makes plants green, now you're down to 6 types of chlorophyll on Earth. So that's a much greater simplification. So we do that, and it seems to serve us well. Myths versus science. Myths try to have an all-encompassing explanatory power. They have a breadth of explanation. And modern day definition of myth is almost synonymous with lie or untruth. That, I don't think that's the correct usage of myth. It is doing the same function for human brain operation as science does. It just has a different anchor points to reality. So science tries to create explanations that have both breadth and depth. So breadth is linking many phenomena at once, depth is explanations, predictions accessible to independent observers. So you're explaining how things came to be to the point we are now, and then predicting where these things are going to be in the future. Whatever the things are, you name a thing or a process, and that's the function of science. But they do share something. They're trying to link many phenomena at once. It's kind of like the difference between scientific medicine and more folk medicine or infomercial medicine. So that scientific medicine tries to come up with a cause of a disease, the pathways that create disease, and then the pathways you can introduce to the system that would take you out of disease. You try to help as many disease items as you can, but usually it ends up being fairly narrow. This medicine treats this condition fairly confined, where your infomercial, such and such a pill, will take care of 500 diseases. The list just goes on for the entire infomercial time. Or if you go to this certain kind of specialist doctor, they will do something to your body that just takes care of everything from headaches to gallbladder stones or whatever. So we see this tug of war between breadth and depth. And what we're going to try to do is build into this as depth to get a theory of everything.
Those two definitions also don't bring into the idea that myths or fairy tales or whatever are more psychological.
Yeah.
Science tends to want to be fact-based, but you want to cure a specific disease. You want to, eradicate, fill in the blank.
Yeah. So
Whereas myths and fairy tales often help to psychologically cope with things and explain the world from not necessarily fact-based. Although I'm sure there are unicorns somewhere.
Oh, sure. But there's often a societal function or a survival mechanism that's built in that does work. And so, if you don't want your kids to get out of bed at night and walk through the house, so they might fall downstairs or get out of the house and get run over by a car in the middle of the night, if there's a monster under the bed, they're going to stay in the covers. So there's a functional reason, even if it's not true. So certainly, so everything can have elements of predictive and functional usefulness. Yeah. So first theories of everything. Try to map where the Earth was and how it formed and what was part of it. This is a neat quote. The human imagination has seldom had before it an object so sublimely ordered as the medieval cosmos. If it has an aesthetic fault, it is perhaps for us who have known Romanticism a shade too ordered. For all of its vast spaces, it might in the end afflict us with a kind of claustrophobia. Is there nowhere any vagueness, no undiscovered byways, no twilight? Can we never really get out the doors? So when you have an explanatory model of the world that just kind of blithely covers everything, where are the avenues of inquiry? Where can your curiosity go? So, but what we focus on in science is cause and effect. We're trying to look at these causal effects. If we'll talk about this in entropy as we go. If I dropped this and film that, which we did, then I held it and released it, gravity pulled it down, it bounced a little bit. If we play the film backwards, you see it bounce and then pop up, something's wrong. So, like how does this all by itself pop up enough to send it back to my hand? It doesn't. It goes in a random direction. Things are very obviously ordered to go in a certain way. We have a cause and effect that we have, through our lifetime of experience, know what's going on. So this is now taking a quick pieces out of our history. So if you were here for the history section, we're going to dip back into this and then go forward into theories of everything, because that's what they were trying to do then. We're still trying to do it now. So this is a bit of a recap of the beginning of this astronomy course. So in pre-Copernican astronomy, we go back to the astrology and the astronomical observations made by the Babylonians, Chinese, and folks in the Arabian region. Aristotle comes along in the 300s BC in Greece, came up with a model, tries to explain everything, famous here, that was good enough for 2,000 years. I mean, yeah, that's name something that we've done this, holding on for 2,000 years. Our country is a baby compared to this. But it's really a philosophy, it's not science. It isn't as anchored to this cause and effect that we're looking for. We had crystalline spheres, no parallax in the stars, so the stars must be all this bowl-shaped sky out here.
Well, maybe it was true, and now it's just changed.
Okay, some more cause and effect we're going to have to bring in to explain that. We know 4 forces, and those weren't even imagined back then, with gravity, electromagnetism, strong and weak nuclear forces. We're going to go in more detail in gravity, then sweep through the other 3 on our way to where science is trying to unify these things. So if we go from way back, 2,000 years minus a little bit back, we jump up to Copernicus. He brought us the heliocentric, sun-centered model of the solar system, and was still looking for perfection up there. Wanted circular orbits, where the real orbits we now know are ellipses or forms of ellipses. So he had to add little things to fix that, but came closer to explaining how the world worked. After that, we have Tycho come along, making a lot of measurements of stars. Saw a new star, supernova, Tycho supernova, which kept chipping away at this perfect universe. So if you have the picture of a perfect universe, as going all the way back to Aristotle, then you, again, don't have these interesting avenues to pursue. You can fill in with, why does this work this way? Well, for it to be perfect, it has to work this way. It's the only piece that fits in. But as observations were made down through the millennia, it kept falling apart, falling away from us. So he made star and planet measurements that were unrivaled, and that set the stage for Johannes Kepler to come along and use the data that Tycho had collected, stole the books actually, and was pursued by Tycho's family for I think much of the rest of his life. But before he was working with real data, he was really fixated on these 5 solids and how they explained the motions of stuff in the solar system. So again, he had this idea, he had a myth that explained how stuff fit together and really did his best to jam it together. Built these things himself and nestled them together to try to work it all out. Once he was working with the data, he had the maturity, I'd say, to abandon that and to go the mathematical route. He saw that planets move faster than the sun and coined the laws of planetary motion. It was very close to actually deriving the equations for mutual gravitation that Newton did later. It's Kepler's 3 laws, that you have a focus, a semi-major axis, you have eccentricity. These all describe the ellipse pathway that things orbit other things. If you mark a point in the orbit, draw down to the focus, and another point, you have the equal amount of area swept out by that segment of orbit in the equal time in another part of the orbit. And so equal area over in equal time. And then that if you measure in years and sun-earth distances of astronomical units, the period squared is equal to the semi-major axis cubed of the orbit. So we have an actual equation now to work with. He didn't know why planets moved. He didn't figure out gravity, but he was getting closer. So it took Isaac Newton, who made a lot of contributions to calculus and optics and physics, to go further. That a body or mass continues at rest in uniform motion unless acted upon by an outside force. So if I'm pushing on this table, the table's pushing back on me. Oh, that's 3, sorry. So I just did 3. 1 is this isn't going to move unless I exert a force on it, which is, again, counter to our day-to-day experience because we live bathed in friction, frictional sources all around us. This is not floating around because gravity is holding it down. It's not sliding off because this table has a roughness to it. When I try to get anything moving, it comes to a stop. And yet, this is really how the universe works. Now, once you account for friction, friction explains why it stops, but that is a different force. So if I go out in space and throw a rock, it's going to go forever. But the big one is F equals ma. The force equals the mass times acceleration. From that, introductory physics is built for students in high school and college. And he came up with Newton's law of gravity. Got to name it after himself. We do that in science. The force between two objects equals minus because it's an attractive force, constant here. The mass of the one body times the mass of the other, divided by their distance squared. So it is a distance squared law of how the force decreases. And we see that in gravity. We see electromagnetism working the same way, twice the distance. You have 1 over r squared amount of energy transmitted. We have other theories that have come along to explain all the forces, trying to pull in gravity and the others. The Boscovich approach came up, he put forward one force that changes its sign depending on how far away two things are. So the strong nuclear force is really close to the atom, so it tracks the weak nuclear force, pops things out of the atom, so you increase the distance and you can pop things apart. Electromagnetism, magnetism pulls if the poles are one way and repels if the poles match. And then you've got gravity pulling together at distance. It is best to formulate how one force that mimics these four, it doesn't work, but it was a nice try. So the other forces are electricity, which we knew about all the way back to 600 BC with static electricity with the Greeks, and the Chinese at 270 BC, they observed electric eels. Of course, Benjamin Franklin's kite idea in the 1700s. Best I can tell, he never flew a kite, but other people did, and some of them died. So we probably wouldn't have had some of Franklin's later contributions if he had not had graduate students. So I'm kidding. That's not. Magnetism, Greek writings around 500 BC show that they were aware of the phenomena. You had Chinese compasses, because you can get lodestone. You can get iron ore pure enough that as through its formation, it locked a magnetic field in it, and you could float that on a little piece of compass in water and see that it finds north. But it took the late 1800s for James Clerk Maxwell. This is the time period that Westworld was supposed to be set in, and they're figuring out the equations to unify electricity and magnetism together into electromagnetism. So we have one force, the photon, one force, and the photon is the particle, if you look at things in a particle fashion, that carries the force. So unification is starting to happen in front of us. So the 99 years of astronomy is this really interesting time period here where you basically get a birth of a science. You have Copernicus up to this point. He puts out his publication on the sun-centered solar system. At the same time, you've got Magellan voyaging around the world. Michelangelo is doing his stuff. Leonardo da Vinci here. Columbus is sailing. You have Tycho and Kepler. So Tycho's taking the data here. Kepler figures out the laws of how the solar system works, how things orbit. Simultaneously, you have Shakespeare, Elizabeth I, Milton Bacon, Guy Fawkes, Rembrandt at the end of this period. Galileo's up here, gets a telescope, perfects it a little bit and starts to observe stuff in the heavens, and publishes his dialogues and is imprisoned a year later. Coming out of this period, you have Newton giving us gravity right here, at least an equation for it. Got Blackbeard and William Penn. After this time period, you've got the French-Indian War. Benjamin Franklin's here with his kite. Boscovich is making his contribution here. So from here forward, we have electromagnetism understood mathematically, with Bach, Voltaire, Mozart, and Beethoven all doing their stuff. There's George Washington up here at the top, American War of Independence. So pretty busy little period of time here in the arts and in science. So what Newton did was, for the first time, explain that a force that we can feel in our backyard is linked to phenomena out as far as you can observe motion in the universe. And Einstein took it further. And of course, as a teenager, you wonder what light would look like if you tried to catch up with it. You were doing that as a teenager. Yeah. So as you run along, does it pool in front of you, or does it, what happens? From that workings, he made the, we won't get to that, E equals mc squared leap using simple geometry and algebra. And in succession, he published on special relativity that shows that time slows and space shrinks at high velocity. And then later, general relativity, that time slows and space shrinks under high gravity. Time and space are warped with gravity, which is where mass and energy are present. This is the leap that nobody else had made yet. Trying to figure out this stuff. We hadn't made measurements yet that showed high velocity items or objects or phenomena have a different rate of time, but he let time change to explain what happens with light. With light staying at a constant speed, something has to give, and it's the flow rate of time. And that was universe-shaking discovery. From there forward, he worked on trying to unify electromagnetism and general relativity. Different ways, different approaches, playing with all sorts of tricks right up to the notebook on his deathbed. So way back, Greek philosophers created the concept of the atom, that there was some smallest unit of material, almost like what we had with the Planck time and the Planck space, or Planck distance. If you get 3 of those, you got a Planck volume. They had the concept of an indivisible smallest bit of stuff. But yet, it wasn't until the 1700s, even into the 1800s, that we began to detect that there really might be a smallest constituent that the stuff around us is made up of. It was highly debated. People argued about everything just being a continuum. Sure, you can break a table in half, but then you just have two table halves. It's because you broke it. It's not because there was something smaller there. It's just, this is the thing, and it's made of table stuff, or wood. But then, yeah, Einstein helped with this debate. In 1905, you had Brownian motion was explained as being the high velocity members of a gas that are jostling dust particles around. What you're seeing is this random motion of particles of dust in the sunbeam coming in the window, which you closed. You ruined my experiment. Is evidence of this atom nature. Pretty quickly, we had the nucleus in the atom figured out by probing into atomic material. And if it was sort of, if atoms were a raisin bread or model like this, we had some little bits inside of particles, and then you have this stuff that atoms are made of, then you'd have particles coming through kind of randomly, passing through uniformly. But what they found was that particles or processes that they probed the atom with would sail right through, but there was some very distinct deflection being caused by something inside the atom that very reliably took a certain percentage of these particles out. So they began to get the model that there was something hard and different in the very core of atoms. And we started to get sort of a solar system model of how atoms work. The Bohr model here, 1913. But quantum physics marched on very quickly, and soon we had a nucleus understood and orbitals that are occupied by electrons, more complex regions where the electrons are found. And much later, suspected in the 30s, but just finally quantified, 1965, the year I was born, was the weak nuclear force. So humanity didn't even know there was what the weak nuclear force was until I was around. It's pretty crazy. Its most visible effect is radioactivity. Like I said, it can help kick components of the atomic nucleus out. The force particles, like the photon was the force particle of electromagnetism, are the W and Z boson. Strong nuclear force wasn't quantified until we were doing disco in the 1970s. It was suspected that something like this was going on back in the 20s. We were able to create, obviously, nuclear bomb by utilizing the release of energy stored in the strong nuclear force and releasable through the weak nuclear force by arranging naturally radioactive elements close enough that they would cascade off each other. So we had nuclear bombs in the 40s.
So John, is that because they didn't really understand it yet? Is that why they didn't know for sure that when they set off that first nuclear bomb,
That it wouldn't start a chain reaction?
it started a chain reaction and just everything?
Yeah, there wasn't a way to mathematically prove it yet. Yeah.
They did it anyway.
I did anyway.
They had
Well,
to know.
yes, that's true. We did know that high energy particles were coming from space, and we could measure radioactivity way back in this time, and they found very rapidly that as you went higher in the atmosphere, you got a significantly larger amount of radiation from above. And so people were trying to explain the source of this radiation simultaneously. So you had the argument that, well, this stuff hasn't set anything off yet, so it must be okay. Which is a very similar argument to when we were about to turn CERN on and people were afraid that mini black holes would be made, fall out of the instrument, go down to the center of the Earth, reside together, start merging, gobbling stuff up, and then snowball until they eat the Earth, and the Earth is a mini black hole, and we're all gone. But you've got very, very, very high energy collisions occurring randomly in the upper atmosphere and have since the Earth had an atmosphere, since it existed. And you have neutron stars throughout the universe that would be much faster reacting to a black hole being made by a high energy particle hitting them, and they would cascade into their own smaller black hole. And we see neutron stars and we're still here. So the argument through indirect observation was, yeah, or it's okay. The universe is already a violent place. We can't break it yet. So
We'll do it slowly.
we'll do it slowly, absolutely. So the strong nuclear force holds protons and neutrons together in the nucleus. Neutrons, of course, don't have an electrical charge, but protons are all positive. Electromagnetism would want these protons to break apart as fast as they can. Very strong repulsion there, but strong nuclear force completely wins. The force particle in this approach is the gluon, which makes sense because it glues things on. These, I think they drank late into the night beers and discussed the physics going on inside the atom so much that we got, strange and charm, and you've got all sorts of very unusual names for these subatomic particles and processes. So like I said before, Einstein didn't like the theory of quantum physics. He didn't like the randomness involved in it. The point that where you push into a phenomena and you must resort to probabilistic outcomes. You can't just say, I drop this, in 3 seconds it hits, makes a noise and bounces up a half inch and then settles down or something. It isn't Newtonian in nature. And special and general relativity cover the stuff that's big. And the stuff that's big is very regular. The orbits of stars, the orbits of galaxies around each other, and centers of gravity of galactic clusters and like that. These are big, predictable things. And down here, it's a very weird world. We haven't even gotten to wave-particle duality and stuff like that, but so he didn't play with that. So as I said earlier, we do now have the electroweak theory. This linked the electromagnetic force and the weak force in 1974. So that's again very, very modern. And this launched the standard model of quantum physics around the mid-70s. So once you have the strong nuclear force quantify the weak nuclear force, you have the electroweak force. Like, you're onto something now. You are now taking observations and you're explaining things up to now. You're generating mathematics that predicts things forward. You're doing science. You're creating a theory that doesn't take care of everything yet, but it takes care of an awful lot. But we are still pushing forward in the grand unification theory. 2011, when CERN came on. Here it is in France, Switzerland. We just were talking about the no black hole problem with this thing. So you have a loop that accelerates particles and feeds it into the larger, I think, opposing beams that are then smashed together. So picture inside, you're working at energies up to 14 tera electron volts. A wavelength, remember I said you have to use higher and higher energy to probe smaller and smaller stuff. So now your wavelength that you're probing is 10 to the minus 19th meters. 10 to the minus 35 is the Planck scale, so you're a long ways away from that. But you're really getting small. Very low temperatures, very high vacuum, so you're not getting collisions that you don't want, and low temperatures, so you're just getting energy from the events themselves. So the beams come along and then are steered into each other to a collision point. And you have, do I have a picture of that? No, I don't have it. So you have huge banks of extremely complex, precise instruments to measure the particles that come out. So the analogy I've heard many times is like you take a couple trillion pickup trucks, one Chevy, one Ford, and you just smash them together. And you're just blasting pieces out of these collisions for hundreds of miles across the landscape. And then you take these trillions and trillions of truck collisions, you pick up all the pieces, and you do it enough, eventually you're going to figure out exactly what the original Ford and Chevy cars look like. And that's what they're doing. So, oh, so violent. So what's it for? We wanted to figure out this Higgs particle, or God particle as it somehow got named, which we have done. Happened in July of 2013, July 4th is the announcement. And this was theorized back 40 plus years ago that there had to be a mechanism through which, again, these virtual particles arise to give some of the particles that we are dealing with mass. The equations work great when the particles are massless. If you give them mass themselves as an intrinsic property, it falls apart. You can't get the mathematics to work. But if you add a field that fills the universe, the Higgs field, which has a corresponding particle, everything is a field and a particle at the same time. You can go back and forth depending on what you need at the time. If you have this particle that can arise out of the Higgs field, then you can explain the math of having mass in some subatomic particles without breaking the mathematics. So he and others derived regions of energy boundary that you'd have to look to find these particles being created long enough to be observed. So if I put enough energy into the table, this is an analogy, it's not really good, but enough energy in this table, it'll start to glow in electromagnetic areas. It already is, but you can think of it that way, that I can make it glow, I can make it give up photons. If you put enough energy into space, then eventually it'll give up a Higgs particle that'll pop out long enough to be seen before it dissipates back. So that was what they aimed for, and they got it, and it was very close to the original predicted values. It was amazing, amazing predictive power of this quantum mechanical model that people were building. Of course, we also want to unify the forces, and we're not there yet. We'd love to look into the nature of dark matter to see processes occurring where once you pick up all the car pieces, you realize there's something missing. Maybe it's the air in the tires. It just merged with the air around once you blasted these pickup trucks together. But can you find missing processes that could then narrow down what dark matter is? And we also have other questions we'd like to answer. When you just work with the Big Bang and its basics, and you start with an empty universe and a quantum fluctuation and this little nothingness of unbelievable energy and pressure comes into existence, and then it expands and particles form out of it. By our understanding, equal amounts of matter and antimatter should be created. And just like those little virtual particles that are particle, antiparticle, they separate, meet, and annihilate, all these matter-antimatter particles should have annihilated each other in the early Big Bang universe, and there should be nothing around. It should be just a big, warm universe that's cooling as it expands. But there was an imbalance. What we call matter won a little bit over antimatter. It's a tiny, tiny fraction, but it's enough to leave us that 4.6% of stuff that stars, galaxies, and computers are made of. Why? We would love to answer that.
Don't you need a collider the size of the solar system to do that?
Yes, to actually probe all the way back to the pre-inflationary grand unification theory and see the processes. I think I've actually heard it's a collider that would encircle our galaxy, so 150,000 light years in diameter. And it would take, let's see, the circumference would be 2 pi r, so 6 times that, so 600, 700,000 years for the beam to go around and the other beam to come around and meet. So you'd have to wait almost 1 million years for your first results to come. You got time?
Millions of years.
Millions. Sure. Not to say that someone won't be doing it, but of course, you've got how many millions of years does it take to build all that, align all the magnets, and what if one magnet's off? All right, you gotta go out there, tweak it, and start the beam again. Okay, my
Create a super huge black hole with that much energy.
Not if you spread it out. But what you can do, though, is since mathematics is predictive, if you can build the foundation, you can start to see the mathematical roots that can then be extrapolated by modeling up into that. Hopefully, that's the hope. So let's look at the unifications we're still trying here. So unification of all the forces. We have electricity, magnetism, and light. Those are all put together in the 1800s as electromagnetism. We have beta decay. That's one way that atomic nuclei fall apart. We have neutrinos that are nearly massless particles that pop out of nuclear reactions. We thought they might be massless, like the photon, so they would travel at the speed of light. They do have a tiny mass, and it was, I think, 1999 that they announced that finding, or maybe 2000. I was doing an internship at NASA Goddard. I was listening to the radio when it came on that discovery had been made. It's like I just stopped right there in the parking lot. I can see the hotel over here and that hotel over there, and it's like, wow, this is big. So I've been waiting for this. We have protons, neutrons, pions, and all sorts of subatomic zoo that we'll talk about in brief. And they are all put together with the strong interaction in the 70s. Oh yeah, these two came together with the weak interaction in the 60s. We have Earth's gravity and celestial mechanics brought together under universal gravity, Newton, 1600s. You link these with space-time geometry, and you get general relativity in the early 1900s. Electromagnetism and weak interaction are brought together in the 70s for electroweak. Electroweak was brought together with strong interactions to the standard model of quantum mechanics. We don't have the grand unification expression yet. We have general relativity and standard model. We don't know what they do. Okay, go to this one. Now, these are the forces, the force carriers. So remember, forces are, you can look at fields, you can look at particles. So we have the gluons for the strong, W and Z bosons for the weak, photons for electromagnetism, gravitons, we think they're there, we don't know, and it'd be for gravity. We have the strong nuclear force, it's understood through quantum chromodynamics. The weak electromagnetism are brought together with quantum electrodynamics. We don't have quantum gravity yet. Quantum electrodynamics, quantum chromodynamics come together with electroweak theory, but we can't unify them yet. And the grand unified theory and the quantum gravity, which we don't have, obviously we don't have a theory for everything. So there's a lot of job security over on this side. So what is it good for? Will it unify the forces? Yes. Will it explain the origin and the end of the universe? Yes, it'll certainly help with that. This is going to your question earlier too. Will it explain life on Earth? Maybe indirectly. Will it explain why you're here? No, that's a little more philosophical. Will it explain why you had eggs and toast this morning? I don't think so. So we find the Higgs particle and we're done? No, because we did and we aren't. See, I'll be working on the largest and smallest objects in the universe, superclusters and neutrinos. I'd like you to handle everything in between. So. All right, so what we'll do next month is we'll get into universal geometry and go deeper into this. There are two deep problems. Gravity is fantastically weak compared to the other three forces. 10 to the 40 powers at a certain unit distance compared to the strong force. If you try to figure out how much energy is in empty space, the error is like 10 to the 120 power or something from taking the standard model and just doing the math. So that's like the biggest error that exists in science between prediction and observation. So we don't see how these get along. We don't want things to blow up to infinity when we do the math. We can't make predictions that way, but that's where the state of the science is. So we'll go up we'll jump into the forces and what we see across the universe with quantum mechanics and general relativity next time. So I'll go back here to that one. Any questions?
You mentioned, and I did the video, that you might try to wrap up by the end of the year,
Oh, yeah.
the course.
But then it just starts over again.
Well, we're going to talk about it. We'll see if we start over or if I go. I can have a whole lecture series on environmental science. I have one.
Oh, I see, just start up a new.
I start a new course, yeah. I've got a geography course I could teach. I have a geology course I could teach. It's fun. Yeah, so I have a biology course I could teach. So we could go other directions. I could also go into my book. I could do a presentation of my book, which eventually I'll be wanting to go on a lecture tour for it anyway. So I could start with a trial audience here if you guys are interested in reality.
Some days yes, some days no.
It's at Robin Williams' Reality. Oh, what a concept. So, all right, any questions, any thoughts? Cold fingers. All right. Well, thank you guys.
Always good.
Deep stuff.
Oh, yes.